Hello, this is Mrs. Ward, and I am going to record the notes for section 1.2, finding the limits graphically and numerically. Know that there are several ways to find the limits, but today we're just going to do it by looking at the graph and by completing a chart. We are also going to talk about the different ways that a limit can fail to exist, and we're going to talk a little bit about the formal definition of a limit and what that means in real-world applications. So let's go. So estimate a limit graphically and numerically. So graphically, what they want you to do is they want you to graph it, obviously. And so here is the graph of x cubed minus 8 over x minus 2. If I look at it, it looks like a parabola. If I'm going back to the note sheet, it wants me to find the limit as x approaches 2. And that should make sense to you, because if I tried to put 2 into this function, I would have 8 minus 8, which would be 0, and then I would, more importantly, I'd have 2 minus 2, which would be 0, and I cannot divide by 0. So to further verify this, if I hit Control-T on my calculator, it's going to show me that at 2 I'm undefined. So that's why I can't do what's called direct substitution. I have to look at the graph. So if I look at this graph, it looks like as I'm approaching 2, it looks like there's definitely a value. I'm going to guess about 12 just based on the graph, but now I'm going to do what's called finding it numerically. So to find it numerically, I want to pick values to the left of 2 and to the right of 2. And by picking values, I don't mean like 1 and 3. That's too big of a gap. I'm going to pick like 1.9, 1.99, 1.999, and then 2.00, 2.01, and then 2. So I'm getting closer and closer to 2 from the right, closer and closer to 2 from the left. So to do that on my calculator, because again, if you go to the tables, right now your delta or your change in x is 1, and you're going to want to leave it like that. You're not going to want to make it 0.0001 because you'd be forever and a day scrolling through there. So what I'm going to do is I'm going to do graph trace. So I'm going to do menu, trace, graph trace, and let's start from the left, and I'm going to do the 1.9. And then I'm going to do 1.99 and get 11.94. And I'm writing these down, by the way. I hope you are too. And then I'm doing 1.999. Going on the other side, I have 2.1, 2.01, and 2.001. And I'm going to write down all those values that I just got from my calculator. And I know I went really fast, but there they are. And so when I look from the left and when I look from the right, I'm going to say that the function, as I'm going from the left and as I'm going from the right, both sides are getting closer and closer to 12. And eventually your calculator will round to 12. So I'm going to say that the limit is equal to 12. And the reason why I can say that is because both from the left and from the right, I'm approaching the same number. So let's do another one. This one I have x squared minus 9, and I'm trying to find the limit as x approaches negative 3. Again, if I tried to put negative 3 in, I would be dividing by 0, and I can't do that. So if I go graphically, I'm going to pick up my calculator, and I am going to graph it, which I already did. So here's this x squared minus 9. It looks like a straight line. If I went to negative 3, 1, 2, 3, and look down, I'm going to guess that it's about negative 6, just based on going from the left and going from the right. But now I am going to actually calculate those values. So going from the left, remember left would be less than negative 3, so negative 3.1, negative 3.01, negative 3.001. From the right would be the negative 2.9, negative 2.99, and negative 2.999. Doing the same thing on the calculator, and you can see that I've already done this, but I'm going to hit menu, trace, graph trace, and then I'm going to type in, what did I say? Negative 3.1, negative 3.01, negative 3.001, and I'm getting those values negative 6.1, negative 6.01, negative 6.001. Now going the other side, negative 2.9, negative 2.99, negative 2.999, and it keeps on adding one more digit. But if I kept on going and made this negative 2.1 just being ridiculous and adding a whole bunch of 9s, your calculator will eventually round it to negative 6. So I am going to say that since I approach negative 6 from the left and since I approach negative 6 from the right, that limit is going to be negative 6. Now, on both of those graphs, when you looked at them, they look like they were continuous functions. They look like there was no breaks or no holes. But that's because the hole is kind of like filled in, if you will. So that's why a limit definitely exists for those two. So this one I have, this is 1 over x plus 1 minus 1 over x minus 4. This one is just asking me to estimate the limit numerically. And when I put that in my calculator, which is on this page here, remember I used my favorite button. I did control divide and control divide again. So I have nice fractions in here, so there's no question of whether or not I graphed this correctly. I want to find the limit as x is approaching negative 3. Well, when I look at this, I see that I have this vertical asymptote at negative 1. That's great, that's wonderful, but that's not what the graph's asking me to do. The graph is asking me to find the limit at negative 3. So this is negative 1, negative 2, negative 3. So I want right in here. So if I hit Control T and I go up to negative 3, I have a value. Who knew? I have a value. So I'm definitely going to have an answer to this. It's probably going to be 1.25. But if I go through the work numerically, like they're asking me to do, I should end up with that same value. I hope I'm having a good day. So I am going to do menu, trace, graph trace, 2.9, and I get that 2.99. And then I want 1. Uh-oh, wrong way. So when I fill in that table, which I did not do, from the left and from the right, they both seem to be approaching 0.0625. Very good. And this one was negative 0.0621. This one. Alright, so when I do this, I get that negative, we're both approaching that negative 0.0625, which oh, it is negative. Oh my, I said that wrong. Okay, I was looking at the wrong thing before. So this one is saying you want to do the limit as x approaches 3, and that's why I get those, and I agree with those answers. When I originally showed you the table, I was looking at negative 3, which is over here, but we're looking at positive 3, which is one of those places that when I look at the graph, I don't see a hole. It's right here is where 3 is. I don't see a hole, but there is a hole, and I should know that there is a hole because I cannot use 3 in here because that would make the denominator equal to 0. Number 4 is an example of a graph where we have the graph, we have the equation. It's a piecewise equation, which is fine. I like piecewise equations. So it's asking me to find the limit of f of x as x approaches 1. So if I'm looking at this graph, and if I'm going from the left, so I'm coming here on this graph, approaching that one from the left, it looks like it's going to be 3. As I approach from the right, it also looks like it's going to be 3. So the limit of f of x as x approaches the number 3 is going to be, as x approaches 1, is going to be 3. because that's what it looks like on the graph. If I asked you what f of 1 was equal to, you're going to tell me that's 1 because I have this dot here. This is an example where the limit does not equal the value of the function. So that's okay, that happens all the time. So the limit of f of x as x approaches 1 is going to be the 3, because from both the left and from the right it's approaching that 3. But if I ask you the value of the function, f of 1, then you're going to tell me that's 1 because that's where that dot is. Okay, number 5, an example of a limit that fails to exist. We'll talk about ruining the surprise. So here I'm going to have, I want as x approaches 4. So here's 4. I'm going to do f of x. I'm going to do from the right. So 4.001, 4.01, 4.1, and then from the left. And when I graph it, I get something that looks like this. So this is the next page. And just to make sure you know how to graph this, let's see. To get the absolute value sign, there's 2 ways you can do it. I always type in ABX in parentheses, or you can hit this button next to the book, and you will see that that's the absolute value right there. Either way you do get there, that's how you get there. So when I'm looking at this, when I do this, and I do the graph trace, all that, from the left, it's going to be, these are all going to be -1. From the right, these are all going to be positive 1. This is obviously going to be undefined. So as I'm approaching them from the left, it's equal to -1. As I'm approaching from the right, it's equal to 1. Again, to highlight what's going on in that graph, you have that big jump. See that jump here and here? Huge jump. So when I have something like that, I'm going to say does not exist. I do not approach the same number from the left and the right, so my limit does not exist. Okay, moving on to the next one, it says unbound behavior. Again, if I graph this, I have the limit as x approaches 0 of 1 over x squared. I know I can't put that 0 in because I will be divided by 0. It's undefined at that point. When I go to look at that graph, I get something that looks like this. So if I do that menu trace, graph trace thing that we like to do, so I'm going to do, I'm approaching 0 from the left and from the right. If I hit like menu trace, graph trace, and let's say I do like 0.1, 0.001, that's that 1 e to 6 is 1 followed by 6 zeros. So if I do 0.00001, that's going to be ridiculous. It's going to be e to the 10, which is a 1 followed by 10 zeros. Huge number. If I do it from the other direction and do a negative 0.01, it's still going to be a positive number. This is e to the 4, so this is 10,000, and I keep on going. So when I look at this graph, and I kind of want to get back to my main window here, when I get to this graph, I can see that as I approach 0 from the left and as I approach 0 from the right, the numbers are getting larger and larger and larger and larger. So I'm not going to approach a certain number. My numbers are just getting larger and larger. So what I'm going to say is that my limit does not exist. And this is an example where I have unbounded behavior. By unbounded behavior, that means that the numbers are getting larger and larger and larger without bounds, or they're getting smaller and smaller and smaller without bounds. Another type of example that does not exist is when you have something called like this. It's called oscillating behavior. So this is where you approach a number and you just keep on bang-banging, like ping-ponging back and forth, back and forth. So if I were to look at this, I think I did this one here when I did 1 over sine of x. When I do this, I go 1, -1, 1, -1, -1. And here's what it looks like in my calculator. You get that. Because, and the reason why it kind of looks like they're connected is because of that whole etch-a-sketch thing when it comes to your calculator. So since I'm approaching 1 and -1, as I get closer and closer to 0, I'm approaching 2 different numbers. This is an example of oscillating behavior. So this limit does not exist either. So those are the 3 limits does not exist in the written here. Is one is if you approach two different numbers from the left side and the right side. So that would be an example of like maps and values. Is definitely one that happens like that. Number two is increases or decreases without bounds. So that's something where like I have a vertical asymptote. That would be an example of no limit. And then the last one is that oscillator behavior. Those are the three times where you do not have to limit. Okay, so now I have some graphs. We're just going to look at them, go real fast. If I ask you to find the limit as x approaches 2, I'm just looking at the graph. As I approach 2 from the left, it looks like it's 2. As I approach 2 from the right, it also looks like 2. So this limit is going to be 2. Again, this is one of these times that if I ask you what is f of 2, you're going to say f of 2 is 0 because that's where it's defined. It's a 0. So that's an example where the limit does not equal the function. This one is asking me to find the limit as x approaches -3. As I approach from the left, it's going down. As I approach from the right, it's going up. So that's an unbounded behavior. So this limit does not exist. More on this page? No. So this one, if I'm asking to find the limit of f of x as x approaches 2, well, as I approach 2 from the left, it's 3. As I approach 2 from the right, it's 1. So this limit does not exist. If I ask you to find the limits of this function as x approaches 4, as I approach 4 from the left, it looks like it's 2. As I approach 4 from the right, it also looks like it's 2. So it's going to be 2. Remember, you can find the limit at any x value if it exists. So, and make sure you're paying attention to what x value tells you to look at. Okay, now the formal definition of a function, in a nutshell, what it's trying to say is in order for me to have a limit, remember how the first one I said, well, that jump of 12 was way too much? What this is saying is that if you vary your x by so much, then there's an acceptable variation in your y. I don't know why it's not very clear. It's really annoying. So if I vary, if this is my x value and I say it's okay to vary this much, then I'm going to have to let my y value vary so much. And I think it's just saying that in order for you to say that they're approaching the same number, you have to decide before you do this, what is going to be an acceptable difference of a number that approaches. Because sometimes it was like, sometimes in these examples, if I go all the way back to this one, like this one was 0.001, -6, and this is -0. So the difference between those two is 0.0001. So I said that was okay. So the formal definition of a limit is that like you have to decide. Usually where this becomes important is like in word problems. So I shouldn't say word problems, but in real life situations, like this one is saying a sporting goods manufacturer designs a golf ball having a volume of 2.48 centimeters. What is the radius of the golf ball? Well, I should be able to figure out that because I know the formula for the volume of the golf ball, of the sphere, I should say. So the volume of the sphere, gotta say that correctly, is 4/3 pi r cubed. Volume of the sphere is 4/3 pi r cubed. So this would tell me the volume is 2.48. So 2.48 is equal to 4/3 pi r cubed. So I took 2.48 divided by pi and multiplied it by 3/4 on r cubed. That should make sense to everybody. And when I did that, I wonder if I wrote it down, but I'll put out. When I did that, I got r cubed to be 5.9205 into r cubed. And then I took the cube of that and I got a radius of 0.839694. that's the radius of the golf ball. Then part B says if the ball's volume can vary between 2.48, so 2.48 would be the lowest volume, and 2.51, which would be the highest volume, how can the radius vary? So then I'm going to say, well, my volume is still equal to 4/3 pi r cubed. Now I'm going to set that equal to 2.51. 2.51 pi r cubed. So I'm going to divide 2.51, divide that by pi, multiply by the reciprocal, so multiply by 3/4, that's going to be r cubed. And when I did that, I got 0.599218 r cubed. Took the cube root of that and got r to equal 0.843066. And this one is actually 0.5. And then, so my radius can vary between 0.839694 inches and 0.843. Makes sense to you. You go to the highest volume, the lowest volume, figure out what the radius is. So in order to get an acceptable golf ball that meets the volume, then your acceptable R values or your radiuses have to be between these two numbers. All right, I hope that helps, and look on Blackboard for your homework, and I will see you next time in class.